Thank you. Okay, so thanks again for the introduction. Yesterday I spoke about minimal graphs. We want to enlarge the perspective and talk about minimal submanifolds in Riemannian manifolds, and I want to introduce one of the most fundamental tools in the study of minimal subvarieties, which is the monotonicity formula. But I will not quite stick to the old monotonicity formula that has been known for a long time, but I will talk about the extended monotonicity formula, which has been introduced about 15 years ago and is in fact a very powerful tool to tackle a number of classical problems in geometry. Okay, so let's get started. So this is lecture 2. And the title is Extended Monotonicity. So again, this fits in the general plan of presenting a number of classical ideas from a contemporary perspective. So the general setting is a Riemannian manifold, which I'm going to denote always by capital X. Okay, and we want the ambient dimension m+1 to be greater or equal than 3. And inside here, we take we take a submanifold. We always postulate, at least for this lecture, to be compact, but possibly with non-empty boundary. And in fact, it's useful to visualize the case of where the boundary is indeed non-empty. So that's somehow the image you wanna keep in mind for most part of this first lecture. And we assume, unless otherwise stated, that sigma is in fact embedded. Okay, and connected as well. So, like we did yesterday in the special case of graphs, we want to look at deformations of this object, and we want to look at the way area varies when we take a deformation. So I first need to tell you the rule of the game, that is to say what I mean by deformation. So the definition is the following. So for me, a deformation is let's say a C2. Well, in fact, C1 would be enough, but some proofs would be a little bit more technical. So let's say the C2 map, which I'm going to denote by capital Phi, from, say, minus delta delta times x into x, satisfying the following two axioms. So the first one is that time equals 0. This is just identity. And the second axiom is that for any t in the interval we are considering, the map phi t, which is a map from X to itself, is a diffeomorphism. And of course, the second axiom is a corollary of the first, modulo restricting the interval delta, but I decided to write them down explicitly just to avoid ambiguities. And at a notational level, to avoid problems in the proof that I'm going to give in half an hour, let me denote by little phi the restriction of capital Phi to sigma. Okay? So for any t, the map phi of t is just a map from sigma to x. Okay? So we just restrict the deformation to the surface to the submanifold we are considering. Okay, so now we want to look at the variations for the area functional, and again we want to appeal to the area formula. So the first form of the first variation formula is the following one. So if we take d dt at t equals 0, of the area of phi t of sigma, well, this is just the integral over sigma of the divergence over sigma, which I'm going to recall in a second, of the deformation vector field V. And what is V? So where V is just the velocity vector field of the deformation at time equals 0. So that's d dt evaluated at t equals 0 of phi t. Okay? Okay, so we will prove this formula in a second, but before proving it, I just wanted to, I want to write it in a way which is somehow more useful in a number of situations, and that's probably the form you're more familiar with. But before doing that, let me remind you of the definition of divergence in this context. So let's say that E1 EM is a local orthonormal frame over sigma. Okay, so then the divergence over sigma of a given vector field, let's say V, is nothing but the sum for I between 1 and m of nabla EIV dotted with EI, where nabla is the Levi-Civita connection in the ambient manifold. And dot is just a simpler notation for G. Okay, so that's when I use this notation, just I'm just referring to the underlying Riemannian structure. Okay, so what is the second form of the first variation formula, which I anticipated? So that's a pretty important computation. And I claim that indeed the divergence over sigma of our vector field V can be written as the sum of two terms, both having a geometric meaning. So the first one is an interior integral, so it's minus the integral over sigma of the mean curvature dotted with V. Second one is a boundary term. So that's again the dot product of the deformation vector field V with the conormal to the surface. So what is the conormal? Well, let's say that this is a piece of my surface or my submanifold near the boundary. So there's a unique outward pointing unit vector field that is tangent to sigma but normal to its boundary. Okay, and that's what I would call the conormal. Okay? So how do you prove this formula given? Well, how do you prove this identity? Okay, that's pretty simple. So let's see why. So the first thing to keep in mind is that somehow when we do a deformation, there are two different ingredients that come into play: the tangential deformation, which does play a role if you do have a boundary, but it's just a reparametrization if you don't, and the normal deformation, which is somehow the most important part. So at a pointwise level, we can certainly write the following thing. So the divergence is just the sum of the divergence of the parallel component plus the divergence of the normal component. And now the two pieces are treated differently. So in particular, the integral of the first term is a purely tangential term. So we can apply the divergence theorem intrinsically to sigma, and that's precisely we get the integral over the boundary of the parallel component dotted with nu. But now nu is a tangent vector, right? So after I get this identity here, I can just forget about the parallel, and just write this as the integral over the boundary of v dotted with nu. Okay, because nu is tangent anyway. And the other term is treated in a little different way. So we want to get the mean curvature out of it, okay, so no problem. So we get the divergence over sigma of B perp. Okay, so now here it's just a matter of keeping in mind the definition of divergence. So we get the integral over sigma of the sum for I between 1 and m of nabla ei V perp dotted with EI. Okay, now V perp and EI are two normal vectors, so if you use one of the axioms defining the Levi interconnection, you can just move the derivative from here to here. So that's equal to minus the integral over sigma of V perp dotted with nabla EI. And that's this. So now I have a normal component here, so I can as well take the normal component of this vector. So let me maybe go here. So that's minus the integral over sigma of V perp dotted with the normal component of nabla EI with a sum where I have a sum here over I. Okay, and this is by definition the mean curvature vector. Okay. Okay, so this is H. But now H is a normal vector, so again I can remove the normal here. Okay, so that's why you end up finding minus the integral over sigma of H dotted with V. Okay. So now there are some special cases of this formula to keep in mind, and in particular I will describe three of those. So the first case that I want to describe is the closed case. So let's agree that a minimal surface for us is just a critical point of the area functional. So now the first case that I want to consider is the so-called closed case. So let's say that d sigma is equal to the empty set. So what's a minimal surface? Well, in this case, it's clear that we don't have the second term there. So in this case, sigma is minimal. If and only if the mean curvature vector is equal to 0. Okay. So an example to keep in mind here is, for instance, an equatorial S2 inside S3. Actually, one of the problems in today's session is that you can't have closed minimal surfaces in R3, or in fact, you can't have closed minimal submanifolds in Euclidean spaces. So you need another ambient manifold, and the simplest example is this one. In fact, let me remark that there's a theorem by Almgren that says that indeed the only minimal immersions of a two-sphere in the three spheres are equatorial ones. So the second case that I want to consider is the case where you do have a boundary, but you keep it fixed. So that's the scenario of the so-called plateau problem. So let's say that d sigma is not empty, but fixed in a pointwise sense, which means, in concrete, that you restrict the class of deformations by adding an extra axiom, and the axiom is that phi, say phi t, is equal to the identity along the boundary of sigma for all t. Okay, so this is the scenario of the plateau problem, and here, there's a lot of examples, but the idea to keep in mind is really the idea of soap bubbles. Okay, so think of having a metal wire fixed, given once and for all. You dip it into water with some soap. Okay, when you extract it, okay, you get a shape of the soap film, which is a critical point for the area functional, at least in some ideal model. Okay, and then there's the third case, which is now a very trendy research area, and which is also related, I guess, to the course that Ilana Fraser will give next week, which is the case where you do have a boundary, and you don't keep it fixed, but you move it according to a certain rule. So it's the so-called free boundary case. So now the boundary is not empty, and the rule is the following. So you work in a class of properly embedded submanifolds, which means the following, that d sigma is equal to sigma intersected dx. That is to say, you want the boundary, you want the ambient manifold to have a non-empty boundary, and you want the boundary of your submanifold to leave the boundary of the ambient. And also you don't want any interior contact points. And you require the class of deformation to somehow satisfy this constraint, which means concretely that you want phi t of dx to be contained in dx for all t. That is to say, you want your deformation to send the boundary to the boundary. Okay. And now, differently from case 1 and 2, in case 3, when we look at the first variation formula, we also need to keep track of the boundary term. And in this case, we have that sigma is minimal when two conditions are satisfied. So let me maybe write it in this box here. So for case 3, sigma is free boundary minimal. If the following two things are true. So the first one is, again, the interior condition, which is the mean curvature must be identical equal to 0. But then you also need, like I said, you also need to take a look at the other piece. And the other piece will be 0 for any deformation vector field, if and only if nu is orthogonal to the boundary of the ambient manifold at each point. Right? So that's the statement that your submanifold must meet the ambient manifold orthogonally along its boundary. Okay? So the reason why that must be the case is that this condition that the deformation send the boundary to the boundary implies the requirement that the velocity vector field must be tangent to the boundary must be tangent to the boundary at each boundary point. And so the only way that this guy here is 0 for any such V is when nu is indeed orthogonal to the boundary of the ambient manifold. Okay, so before proving the first variation formula that I wrote here, let me also make a remark about the link between these formulas and the higher isoperimetric problem. So let's take the identity that I wrote there, and let's take the deformation vector field given by the identity. So take V of x just equal to x. And so let's compare now the left-hand side and the right-hand side of that identity. So I claim that the divergence over any m-dimensional submanifold sigma, not necessarily a minimal one, of this vector field is just equal to m. So this is a simple computation in the homework. So that formula implies, so let me call that formula star, implies the following identity. So m times the integral over sigma of 1, so that's nothing but the area of sigma, or if you want, the m-dimensional Hausdorff measure, is, well, let's say that we look at minimal submanifold. So let's say that sigma is minimal. So the first term on the left hand, on the right hand side will be equal to 0, and on the right hand side we get, say, something like a bound of the form the diameter of sigma times the m-1 dimensional measure of the boundary. Okay? Right, because I'm just doing the trivial estimate for the boundary term. But now a key remark here is that it was proven by, so let's look at the constant here. So it was proven by Allard in 1972, and in a somehow stronger form by Michael and Leon Simon, I guess in 73 or 74, that indeed one can get this inequality with a constant here which is purely dimensional. So a constant that doesn't depend on sigma. So in fact, what I'm saying is that one can prove that, say, the m-dimensional Hausdorff measure of, say, a minimal surface can be bounded by a universal constant, which is only a function of m, times the m-1 dimensional measure of the boundary raised to the right power to get scaling invariance, which is m over m-1. And one of the problems that I suggest today is to prove this interesting inequality when m equals 2. Okay, that's pretty easy, in fact. Now, a key remark that I want to make, which is, again, in the spirit of showing how easy it is to get to open problems, is that the optimal value of this constant, in general, is not known. Right, so that's precisely a higher isoperimetric problem. So you look at m-dimensional submanifolds in the Euclidean space of dimension m+1, okay, and say you normalize the length of the boundary, maximize area. Well, we don't really know what's the optimal value for general codimension, okay? We do know when sigma is area minimizing or in special dimension, but we don't know in general, okay? And there's various contributions by, so special cases are done by Almgren, I guess Lee and Shane, and a bunch of other people. Okay, but the problem is open in general. Okay, so now let me sketch the proof of the monotonicity, sorry, of the first variation formula, which I wrote here. So let me call this maybe sharp. So there's an interesting remark here, which I guess is not so well known in the literature. So I claim that it's enough to prove this formula when the ambient Riemannian manifold is the Euclidean space, which makes the proof a lot simpler. The price that you need to pay is to work in general codimension, okay? So we want to prove this formula for an n-dimensional submanifold in Rn+1. Now, I will prove it in this special case. Now, the way you can reduce the general case to the special case is using Nash isometric embedding theorem in the smooth category. But of course, there's a little extra argument there because you need somehow to compare different mean curvatures, the mean curvature of sigma inside X, and mean curves of sigma inside some high-dimensional Euclidean space. Okay, but I claim that it's pretty easy actually to reduce the general case to the Euclidean case. So let's prove the formula in the Euclidean case. Okay, so we need to again to get back to the area formula. Okay, so the left-hand side, okay, will be equal by the area formula to the derivative evaluated at t equals 0 of the integral over sigma of the square root, and here we will have the determinant of d phi t transpose times d phi t. And now we just need to compute these terms here. So first of all, we take phi of t and we expand it as a function of time. So phi t at p will be equal to p plus t times v at p. Now remember that v is the velocity vector field plus an error term, which will be little o of t. And so when we differentiate, we get that d phi t at p, say evaluated along some vector field ei, okay, is going to be equal to ei plus t times d eiv, where capital D is the Levi-Civita connection in the Euclidean space, so it's the flat connection, plus an error term, which again I'm going to write as little o of t. And so now I claim that so given these two formulas here, the expression I wrote there is equal to the integral over sigma. And so let's see, I will get, well, the denominator is gonna, given that I'm evaluating at 0, I'll get twice, and then I get the square root of the determinant of the identity, because I'm evaluating at t equals 0, so I get 2 times 1. And here I will get just the derivative at time equals 0 of the determinant of d phi t transpose d phi t. And now I claim that we can write the numerator in the following form. So let's open a box here. So I claim that let's forget about the determinant for 1 second. So I claim that the matrix d phi t transpose times d phi t, so I claim that the derivative at time equals 0 of d phi t transpose times d phi t is just going to be equal. Okay, so let's see. Well, let me keep the dependence of t because I don't want to skip a step here. So this is just going to be equal to, let's see. So I get a square matrix here. I claim that the ij term is going to be equal to ei plus t d eiv plus little o of t times ej plus t djv plus little o of t. And so here I will get, the first term will be just dij, so Euclidean, plus t, so here I have div dotted with ej, plus dej v dotted with di plus little o of t. And so now I just need to keep in mind the way one can differentiate the determinants. Let me open a box here. So it's a general fact, which you can prove using some basic calculus, that the determinant of some identity matrix plus t times n is just going to be equal to 1 plus t times the trace of m plus little o of t. And so now so when I take the derivative, okay, I will only I will only see the trace, so I will only see the first order term. And the first order term is nothing but the trace of this yellow box. And so it's going to be twice the divergence of the vector field V over sigma. So the factor 2 will cancel with the 2 in the denominator, so I get the integral over sigma and the trace of that guy, which is precisely the divergence over sigma of V, which is what we wanted to prove. Okay. So that's the way the area function changes to first order. Now there's something magic that happens when you compute the first variation, which is precisely that the monotonicity formula holds. And when we have a monotone quantity in geometry, we like it because monotone functions do have limits at any point, okay? And that's somehow related to the notion of tangent density to a variable, which I now want to describe. So the setting is again the one that I wrote here.
Alessandro, would you mind moving the bottom boards up? When you're finished, would you mind moving the bottom boards up so people can see?
Like this?
Why don't you just switch?
Okay. You want me to invert them. Okay, good. Okay, thanks for the remark. So we have a saying in Italian which is about that from the suburbs you see the center better, you know. So thanks for helping me from the suburbs of the room. Okay. Okay, so let's get back to mathematics. And so let me say something about monotonicity now. So the basic idea to have in mind is the following. We are in Rn plus 1 with the flat metric. Okay, and here we take some submanifold sigma of dimension m. M is between, say, 2 and n. And we allow that sigma to have a boundary. Okay? So pick a point P in the ambient space and define the following number R bar to be just the distance in R3, so in the ambient, sorry, in Rn plus 1, between P and the boundary of sigma. Okay? That's some number. Let's say it's not 0, otherwise the story is not very interesting. So the fact, which is indeed the monotonicity formula, is that the following quantity, so we take the ratio between sigma, the area of sigma contained in the Euclidean ball centered at P and having radius R, and the corresponding area for the m-dimensional disk. Well, the statement is indeed that this quantity is non-decreasing. And actually, we do understand the case when the derivative is 0 very well. So this conclusion is true for little r between 0 and capital R. And I will get to this point in a second. And the equality case is the statement that if the derivative at some point R equal R naught exists. So if that function is differentiable at R naught and the derivative is 0, then, well, in fact, it's an equality, it's an equivalence, then we do know that sigma will meet the sphere centered at P and having radius R orthogonally. Actually, we do have an explicit formula for the remainder term, but for the purpose of this lecture series, I don't really want to embark in studying the remainder term. So what we need to keep in mind is somehow when we do have derivative equal to 0, we must meet the Euclidean ball orthogonally. So what is the most immediate application of this fact? Well, the most immediate application is that we can define densities. At all scales. So we define capital theta of sigma with respect to a center P and the radius R, just to be the ratio that I wrote there. And now, what we do know for sure is that this function has a limit at 0. So we can define the density at P to be just, which is denoted by theta sigma P0, to be just the limit for R going to 0 of the density at scale R. And for instance, at a smooth point, you will get density equal to 1. But when you have a non-smooth point or you work in a very full setting, then this number contains a lot of interesting information about sigma. And if the number R bar is equal to infinity, which means that the boundary of sigma is empty, which would be the case of complete non-compact minimal submanifold, well, then you can also take the limit at infinity, which is typically denoted just by theta sigma. So that's the limit for R going to infinity of the density at scale R. And of course, a priori, this number does depend on P, but it's easy to prove, and again, it's one of the problems today that it does not. Okay, because if you take 2 points, well, the ball centered at the first point with the radius R, a very large number, is very, very close to the ball centered at the other point. Okay? And these two balls will get closer and closer as you send R to infinity. Okay, so that's pretty much the reason why this number is well defined. And so just to play a little bit with this number, let me prove a simple rigidity theorem about densities. So let's take it as a simple application of the monotonicity formula. So the idea is that if we have a complete minimal submanifold, so no boundary, then the density at infinity contains a lot of information about the submanifold in question. So let's see a simple theorem in this direction. So let's say that in the setting above, let's say let sigma m be a complete minimal submanifold. So in particular, the boundary is empty. Okay? So the statement is that theta of sigma is always greater or equal than 1, and that's not a big deal. Okay, but the interesting part is the rigidity statement. So what can we say about complete minimal submanifolds having density at infinity equal to 1? I claim that this happens if and only if sigma is an n-dimensional affine plane. Okay, so the proof is very simple. Let me just sketch it. Okay, so the fact that the density is greater or equal than 1 is almost trivial, because at scale 0, okay, the density is essentially, well, is equal to 1 if you are in embedded category, and if we were working with immersed objects, it would be greater than 1, or greater or equal than 1. So let's discuss about the equality case. So if theta of sigma is equal to 1, then we must have that the density at scale r must be equal to 1 for all r, right? And so, in particular, this function, as a function of r being constant, is differentiable at any point with derivative 0. Which implies that sigma must intersect each ball in the Euclidean space orthogonally. Okay? And so when sigma intersects each ball orthogonally, then sigma must be a cone with respect to P. Okay? Which means it must be invariant under dilations. Okay, but then recall that sigma is smooth. In this course, sigma is smooth. So in particular, the only way it's conical and smooth is when it's actually affine. Okay. So that's somehow the old part of the story. Now I want to get to the new part of the story, which is the extended monotonicity. Now the motivation for talking about extended monotonicity is extremely simple, and is related to this little white box that I drew here. The monotonicity formula is only true for a given point P as long as you don't touch the boundary. To convince yourself about this, let's think about the case when sigma is compact with a boundary. So think about the solution to the plateau problem. Well, we fix a point P. Well, when R is large enough, the numerator in this ratio will be constant, right? Because there's a radius such that you already enclose all of the mass, and as you make R larger and larger, there's no extra mass anymore. So beyond R bar, if sigma is compact, then the numerator will be constant and the denominator will keep growing. So there's no way that the formula is true beyond the boundary. And so in 2002, Ekholm, White, and Winholz discovered that there's a way of going beyond the boundary. And I would like to tell you something about this idea. So let me first explain their result with a picture. The picture is the following. So let's say that again we have a minimal submanifold of dimension m. And let's say that the boundary is not empty. Okay, if the boundary were empty, then R bar would be infinity. So let's say that this sigma is some guy. Let's call it gamma. So let's pick a point P which does not belong to gamma. Okay, so we can consider the cone, which I will denote by E, over gamma with center P. So by definition, that's nothing but the set of points of the form T times V, where T is a non-negative real number and V is in gamma. So that's the cone over gamma. Let's say that without loss of generality, let's take P to be the origin, right? So otherwise, you should just take V minus P. Okay, that's fine. And then let's take the so-called exterior cone, which I'm going to denote by E prime, which is nothing but the part of E that lies beyond gamma. Okay, so that's T times V, where T is greater or equal than 1, and V is in gamma. So that's the exterior cone. And then let's consider the following object, which a priori is not smooth, and in fact it won't be smooth. So let's call sigma prime just the union of sigma and the exterior cone over its boundary. So we have this object with a boundary, and we sort of remove the boundary, we complete it with the outer cone. So the monotonicity formula says that the density of this guy, which is not smooth and not minimal, is indeed a non-decreasing function. So the theorem by Eckel, White, and Vinolf, 2002, says that indeed the density of sigma prime is a non-decreasing function, and we do understand the equality case. So in the usual form, we will have that the derivative at some r equals r naught of the density is equal to 0 if and only if the following two things are true. So the first one is that the normal, so at this point, at scale r, the normal to sigma must agree with the normal to E prime. That is to say, the conormal, say, to d sigma plus the conormal to d E prime is equal to 0 on gamma intersected db pr. And the second condition is that sigma prime, so it's the same condition we would have in the smooth case, sigma prime will intersect the boundary of the ball of center P and radius R orthogonally. So let me show or try to convince you about how powerful this method is by discussing two applications which are completely out of reach without this tool. So the first application is about the following question. So let's say we are in the Euclidean. Well, let me actually state it in the simplest possible case. Let's say we are in R3, and we take a boundary which is made not just by one curve, by multiple curves, let's say 2. Okay, so the picture is that we have a curve gamma 1 here and another curve gamma 2 here. Actually, what I'm going to say is true for m-dimensional boundaries in n+1 dimensional Euclidean space. So it's true in any codimension. And let's say that we want to solve the plateau problem for this boundary, which is disconnected. So the question is, will we find connected solutions or only disconnected ones? Well, the heuristics is that let's take two circles. Well, if the two circles are very close, and you take your wire and dip it into soap film and set it in soap water, you will find a piece of catenoid when the two circles are very close. But then as you move them and they get farther and farther apart, then somehow you will go from a stable to an unstable regime, and you will not find a catenoid anymore. You will find two flat disks. Okay, so what is the corollary here? Is that there exists a constant d0, which is actually universal, so it only depends on the length of the two boundaries. So d0 is just a function of the length of gamma 1 and gamma 2. And again, this is true in any dimension and codimension, such that any, so I'm not saying one minimal, any minimal surface, or minimal, well, in this case, minimal surface, sigma 2, or sigma, such that the boundary of sigma is equal to the disjoint union of gamma 1 and gamma 2, is disconnected. Okay. So no matter the shape of the boundaries, just depending on their length, if the two boundaries are far apart, there's no way you can join them with a minimal surface. Okay. And this is a pretty easy application of the extended monotonicity, which is again, completely described in the problem set. What's that? Oh, yeah, sorry. Thanks a lot. So is this connected provided or if the distance in R3 between gamma 1 and gamma 2 is strictly larger than d0? Thank you. Yeah. Okay, so that's application number 1. Oops. Let me go to an even more striking application, to a classical problem in knot theory. So the starting point for such application is the question about the complexity of a curve in R3. So how do we measure the complexity of a curve in R3? So well, certainly there's multiple answers, but there's a pretty natural notion. So let's say that gamma is a map from S1 into R3. Okay, so we can measure its complexity by just taking the integral over S1 of its curvature as a submanifold in R3. Okay, so if we parameterize it by arc length, then essentially the second derivative of this map, okay, will measure the curvature of the image as a submanifold in R3, okay? And so at each point we have a curvature, we can integrate and we get a number. So let's say for instance, we want to compute that number for a flat circle, we'll get 2 pi, okay? But in general, if we get curves that wiggle around a lot, then you get larger numbers. So the question is whether we can correlate that number to the fact that the curve is a knot or is isotopically trivial. So there's the following theorem, which was first proven by Ferry and Milnor in 1950. with a topological proof, which is that if that number, so the total curvature of the curve is less than 4 pi, then the curve in question, so let's say gamma of S1, is unknotted. That is to say, it is isotopically trivial. And again, this is a pretty straightforward application of that result. So just at the heuristic level, the point is the following. So the reason why, so we can give a proof of this result using minimal surfaces. So we can prove this result, which a priori has nothing to do with minimal surfaces, just using minimal surfaces, because of the following fact. So we can prove the following, that if this condition is true, so if the integral over S1 of the total curvature is less than 4 pi, well, we can prove that any minimal surface with this boundary must be embedded. So any sigma 2 with boundary of sigma equal to the curve in question must be embedded. So in general, when you solve the plateau problem, even in ambient dimension 3, it's not true, and it's not clear and not true in general that the solution that you find is actually embedded. You can have self-intersections. But certainly, using the extended monotonicity, you know that if this number is less than 4 pi, well, any solution, so in particular, say the disk-type solution, which was obtained by Douglas and Rado in the 30s, must be embedded. So in particular, you can find some solution to the plateau problem, which is an embedded disk. And you can use this embedded disk to take your curve and shrink it smoothly to a point. So in particular, there cannot be any topological complexity. It must be, so this is sort of a concrete and effective isotopy between your curve and say a point inside it. Okay, so in the remaining time, I just want to sketch a very simple proof of the classical monotonicity formula, which I guess has the advantage of making it clear why that formula is true. So if you take a look at classical textbooks in, say, geometric measure theory, well, you will find very accurate proofs where you have a nice remainder term, which is pretty much explicit. But my feeling is that somehow those proofs sometimes tend to hide the reason why the monotonicity is true. And actually, the proof that I'm going to give has the advantage that you can prove the extended version with very minor variation. So if you understand this proof, then you will be able to prove the extended version this afternoon without any problems. So the proof is gotten by combining two inequalities. So let's get here. If you remember, we proved when talking about the higher isoperimetric problem, we were talking about the identity that the integral over sigma of the divergence of x is equal to minus h dotted with x plus the integral over the boundary of x dotted with nu. So now, if you have a minimal submanifold and this guy is 0, okay, we know that this guy is m times the area. And the right-hand side, can be bounded by, say, like I said, the diameter of sigma times the length of this boundary. So now, in order to prove the monotonicity formula, let's apply this formula here to sigma intersected BPR. And let's assume to make things simpler that in fact this is a transverse intersection. Okay, otherwise you need a little bit more care, but the proof is essentially identical. So let me call A of R the area of sigma intersected BPR, and let me call L of R the length of sigma intersected the sphere centered at P and having radius R. So in particular, if we replace sigma by sigma intersected with a ball of radius R for R less than R bar, okay, we get M times A of R is less or equal than R times L of R. Okay. On the other hand, I claim that for any R, if the intersection in question is transverse, then we have that A prime of R is greater or equal than L of R. So this is the second inequality here is a consequence of the co-area formula, and we can justify it very rigorously. But the idea is very simple. So let's say that I have my curve, my boundary curve here, and I take a slight fattening of the curve. So I compare A at R plus dr with A of R. So well, you can convince yourself that this difference is at least L of R times dr, right? And you're going to have equality when somehow your surface meets the boundary of the ball at center at P and having radius R orthogonally. Okay, but you can justify this inequality with the co-area formula. So now let's combine these two things together. Okay. So if we combine these two things together, we get that M times A of R is less or equal than R times A prime of R, right? And so this is the same as M over R less or equal than DDR log A of R. And now we take this inequality, we integrate it between, say, R1 and R2, and I claim that you precisely get that A R1 over R1 to the M is less or equal than A R2 to the M, okay, which is the monotonicity. And you can study the equality case without problems. Now, let me take 1 minute to justify this step here, just for completeness. So the way you justify it is with the co-area formula. Let's say that this is sigma. Okay, the co-area formula is about integrating by slicing. So we take a height function h. Okay, and what the co-area formula says is that the integral over sigma of a function f in dhm is equal to the integral, well, let's say between 0 and infinity of the integration over the level h equals s of f divided by the gradient of the height function dh m minus 1 ds. So now let's apply this formula here with h of x equal to the length of x as a Euclidean vector, and let's take f equals 1. Okay, so we get that the integral over, well, okay, let's say we replace sigma with sigma intersected BPR. The integral of 1 is equal to the integral between 0 and r of the integral for h equals s of 1 divided by gradient of x h m minus 1 ds. Now we differentiate in r. Okay, so if we differentiate in r, we will get that the a prime of r in the notation above will be equal to the integral for h equals r, sorry, x equals r of 1 over the gradient of sigma of the function f dh m minus 1. But now the term here I have here at the denominator is less or equal than 1. That's pretty obvious, right? So in particular, this is greater or equal than the integral for h equals r, x equals r, of dh m minus 1, which is what I call LOR. Okay, and so this concludes the proof of star, and therefore the proof of the monotonicity formula, which I claim is the right way of thinking about and proving the extended version as well. Thank you very much. Well, in general, you will have solutions that are either of disk type or non-disk type. But what you do know for sure is that you do have a disk type solution. You may have solutions with a different topology, but by Douglas and Rado, so like just a mapping perspective, you do have a disk. That disk in general is immersed. But in this regime, that disk must be embedded. So what you do know for sure is that there's a minimal disk which is embedded and there's this given boundary. Okay, so that you can use that disk to shrink the curve to a point.
So the curvature equals to 4 pi.
Right, so this value is sharp. Actually, with a little bit more effort, you can prove that this is true. Okay, but that's a little bit delicate. And in fact, this value is sharp. So for any epsilon greater than 0, there are examples, there exist examples gamma epsilon from S1, azimuth as you want, which have total curvature equal to 4 pi plus epsilon, but are isotopically non-trivial. Okay, so the idea is that you can double an S1. So you take two S1s, you go from one to the other, with a normal crossing, and then for sure you will have curves that have total curvature as small as, well, as close to 4 pi as you want, but they are not trivial, and indeed, well, so for these boundaries, any disk must be, any minimal disk with that boundary must be immersed.
What's the high-dimensional inequality optimal?
What do you mean by optimal? So like I said, so we can prove, and in fact it's pretty easy using the tools that we discussed that you do have some constant. Now the problem of determining the optimal constant is open in general. It's known only if sigma is area minimizing, which is a lot stronger than minimal, or is also understood when sigma has dimension 2, so in the surface case, but in general is completely unclear. So of course it's conjecture that C of m should be the constant that you get for an m-dimensional disk living in some affine plane, but that's very hard. I mean, I don't know how to prove it for sure.
In the space, not using the space, the constant depends on the m and the curvature.
Yeah, for sure. Yes. Yeah.
Any other question?